Hello, good morning. Uh, I am Sachin Charbe. So, last lecture we studied the introduction of oscillators. Okay, Mm, there are the types of the oscillator also we studied. So, in that type, so we will see the detail of the phase shift oscillators. Okay, in phase shift oscillator, this is the this phase shift oscillator. Here the amplifier we use, that is op amp, and the feedback circuit, that is RC feedback circuit. So this is the idealized phase shift oscillators diagram. Now the question is that what is RC phase shift oscillator? RC phase shift oscillator circuit can be built with a resistor as well as a capacitor, and in LC phase shift oscillator, that is built in inductance and capacitance. These circuits offer the required phase shift with the feedback signals, and they have the outstanding frequency strength and can give the clean sine wave for an extensive range of loads. Okay. Now an example of an oscillator circuit that follows the basic development of the feedback circuit is the phase shift oscillator, and idealized version of this circuit. So this is the diagram of the idealized version of the RC phase shift oscillators. The requirement for oscillations are the loop gain beta A is greater than unity, and that is the phase shift around the feedback networks. Okay. So oscillators work on the criteria, that is the Barkhausen criteria. If A beta equals to 1, we will get the sustained oscillations. If A beta is less than 1, so we get the damped oscillations, and A beta is greater than 1, that is the undamped oscillations. So for sustained oscillations, beta A is greater than unity. In the present idealization, we are considering the feedback network be driven by a perfect source, that is zero source impedance, and the output of feedback network can be connected in a perfect load. So perfect load means the infinite load impedance, if the load impedance is infinite. The idealized case will allow the development of the theory and the operation of the phase shift oscillators. Phase shift oscillators are interested in the attenuation of the network frequency at which the phase shift is exactly 180 degree. So classical network analysis, we find that frequency of the phase shift oscillator, that is 1 by 2 pi RC under root of 6. So in beta, that is feedback element equals to 1 by 29, and phase shift is 180 degree. So for the loop gain beta to be greater than unity, and gain of amplifier stage must be 1 by beta or 29. That means gain is greater than 29. When considering the operation of the feedback network, one might naively select the values of R and C to provide the specific frequency. So each will get the 60 degree phase shift for section for 3 section, and result, that is 180 degree phase shift as desired. If one measured the phase shift per RC section, this section would not provide same phase shift, although the overall phase shift is 180 degree. If it were desired to obtain exactly 60-degree phase shift for each three stages, the emitter follower stages would be needed to each RC section to prevent the each from behind loaded from the circuit. So in amplifier we can use the FET, BJT and op-amp. So next example we are taking the FET phase shift oscillators, field effect transistor, where the drain resistance RD, then source resistance RS, that is the amplifier, and in feedback element, that is the RC networks, and overall the frequency will be get, that is 1 by 2 pi under root of RC, and the output of that amplifier is feedback to the feedback circuit, and output of that feedback circuit again given to the input to the FET via the gate. Then next diagram is the BJT phase shift oscillator. So in BJT phase shift oscillator, that is the common emitter amplifier with voltage divider. R1 R2 is the voltage divider circuits, RC, then VCC and RE and C. C is the bypass the emitter resistor, that is RE. Again the frequency will get the same, that is 1 by 2 pi RC and into 1 by under root of 6 plus 4 into RC by R. Then R dash C, RC and RC, that is feedback network. So we will see detail. A practical version, we are see detailing of the FET phase shift oscillator. Practical version of phase shift oscillator circuit is shown in figure. The circuit is drawn to show the clearly amplifier and feedback network. Amplifier, that is FET, and feedback network, that is RC. Amplifier stays cell bias with the capacitor by bypass source resistor RS and drain bias resistor RD. So, mode of gain A, that standard gain of the amplifier we studied in the amplifier, that is GM into RL. Transconductor into load resistance, where RL in this case the parallel resistance of RD and small RO. Then RL can be calculated equals to RD, capital RD into small rd, that is divided by RD plus small rd. Small rd is nothing but the internal input impedance of the FET. The output impedance of the amplifier stage, that is given by RL, should also be small compared to impedance seen looking into the feedback network, so that the attenuation due to loadings occur. Next we will take the one example, dear student. In this type of example, maybe as there should be some data changes. So this example is depend on the FET amplifier or FET with phase shift oscillator example, that is it is desired to design a phase shift oscillator as in figure. So you can refer this FET with RC phase shift oscillator. Okay. Using an FET, transconductance value is given, that is 5000 microsecond, small RD equals to 40 kilo ohms, and a feedback circuit value R equals to 10 kilo ohms. Select the value of C for oscillator operation at 1 kilohertz and capital RD for attenuation 29 to ensure the oscillator action. So this is the design of the phase shift oscillator. Some data is given, some internal parameter is given. Now we have to solve this numerical, solve this example. So we have to use the equation, that is the frequency, that is f equals to 1 by 2 pi RC into under root 6. Using this we can calculate the capacitor value. So 1 by 2 pi RF into under root 6. Now we have to put the value 1 by 2 pi, then put the value of R, that is 10 kilo ohm, then frequency, the value of frequency is given 1 kilohertz. In this way you can calculate the capacitor value. So we are getting the value, that is 6.5 nanofarad. Now we have to use the equations of the gain of the amplifier and load resistance equation, that is we already seen in the previous slide. Okay, gain can be calculated by GM into RL, and RL equals to capital RD into small rd divided by capital RD plus small rd. So put the value RL, first we have to calculate the value of gain. So put the value of GM is given 5000 microsecond, and RL, so we have to first calculate the value of RL. RL can be calculated by RD into capital RD, small rd into capital RD divided by capital RD plus small rd. So you have to putting the value, you can calculate the value of RD. So RL load resistance is given, and we have to calculate the value of the load resistance. We have to solve it for RD equals to 10 kilo ohm, that value is given 10 kilo ohm, and small rd is also given. So using that we have to calculate the capital RL. So if you know the RL, then we can calculate the gain also given. So GM into RL. So using this you have to calculate the RL. So we will get RL equals to 8 kilo ohm. So in this way you can solve the design numerical of the RC phase shift oscillators. Now the next slide is transistor phase shift oscillators. So instead of FET, here we use the transistor Q1, then the first RC, that is given the 60 degree phase shift, second RC, that is given the 120 degree phase shift, and third RC, that is 180 degree phase shift, and this amplifier also give the 180 degree phase shift. Okay. So in the circuit diagram, resistor R1 and resistor R close to base of the Q1. Okay, resistor R1 and R close to base of the Q1 gives the voltage divider bias. So that is used for voltage divider bias. Resistor RC limits the collector current, as we know that, while the R is meant for thermal stability, that small Re or emitter resistance. C is emitter by a bypass capacitor. C out is the output DC capacitor. By using more than 3 RC phase shift stages, like the 4 into 45 degree, the frequency stability of the OS is improved. The frequency of the oscillators can be expressed by, so frequency can be calculated equals to 1 by 2 pi into RC under root of twice n. So small f can be equals to f equals to 1 by 2 pi RC, 1 by under root of 6 plus 4 into RC by R, and the HFE can be calculated. HFE is greater than 23 plus 29 R by RC plus 4 into RC by R. So for this you can refer the Boyle's stat. Okay, so in this way, so transistor phase shift oscillators. So some short notes may be asked. So transistor phase shift oscillators. Then next slide is RC phase shift oscillators using op-amp. So here in the amplifier we are use the op-amp circuits. Okay, this op-amp is the inverting mode. We are using in the inverting mode Rf by R1. So minus Rf R1 by minus Rf by R1. That is the V0 by Vi. Then RC networks. Okay. So this is the phase shift oscillator using op-amp. The circuit diagram RC phase shift oscillator is shown above. The feedback resistor RF and resistor R is used to set the gain of the oscillator. So we know that we will get the gain. How to calculate the gain? That is the output by input, means VO by Vi. That is nothing but the minus Rf by R1. Why minus? Because we are using the mode that is inverting mode. The three stages phase shift network comprising of R and C that produce the 180-degree phase shift. This is RC network. Op-amp itself wired in inverting mode produce the another 180-degree phase shift. Thus, the required phase shift is of 360 degrees, often between input and output. So in this way we covered FET based RC phase shift oscillators, DCT based RC phase shift oscillators, and op-amp based RC phase shift oscillators. We cover the design numerical of the FET. Similarly, you can use the design, you can try to solve the numerical of DCT and op-amp base also using the formulas. Now the advantage of the RC phase shift oscillators, this is the generalized advantage. So first advantage is oscillator circuit designing is easy with the basic components like resistor as well as the capacitors. This circuit is not expensive and gives the excellent frequency stability. Third, these are mainly suitable for low frequency. That also we already studied in the previous lectures. According to the frequency wise, we seen the chart. Fourth, this circuit is simpler compared with the Wien bridge oscillators because it doesn't require the stabilization, planning and negative feedback. Then fifth, circuit output is sinusoidal, that is somewhat distortion free. Sixth, the frequency range of this circuit will ranges from few hertz to hundreds of kilohertz. Now there are some disadvantages of the RC phase shift oscillators. There are the four disadvantages. The output of this circuit is small because of smaller feedback. It requires 12-volt battery or power supply for developing a suitably used feedback voltage. It is hard for this circuit to create oscillation because of small feedback. Frequency stability of this circuit is not good to compare with the Wien bridge oscillator. So this is the main disadvantages. Now the application of RC phase shift oscillators. This phase shift oscillator is used to generate the signals over the extensive range of frequency. They use in musical instrument, in GPS unit and voice synthesis. Second, application of phase shift oscillator includes the voice synthesis, musical instrument and GPS unit. So this is repeated. So thank you.